Welcome to this deep dive. Our mission today is to explore what initially looks like a nearly invisible programming dilemma.
Yeah, it really just starts as a few lines of code from a developer's blog.
Right. But it rapidly unravels into this incredible, complex look at language architecture and the underlying quirks of how text is rendered.
And I think it also highlights the immense friction involved in modernizing legacy computer systems.
Absolutely. So we're pulling today from a set of notes written by a developer named Ang. Specifically, it's a post titled Notes-on-Haskell-Programming Part 205.
A very detailed, ongoing series, yeah.
Yeah, exactly. So to set the scene for you, imagine you are Ang. You're building this command line utility called XS2Book, which is it's designed to generate ebooks from plain text files.
Right, a pretty standard tool.
Exactly.
Yeah.
And you simply need to add a command line argument for the user to set a publisher name. Like literally just a publisher flag.
This is a totally standard feature for any file generation tool. You know, you want to embed metadata.
Right.
And if the user doesn't specify a publisher, the program needs to seamlessly supply a default one.
Okay, so to understand how this seemingly simple task goes completely sideways, imagine you walk into a coffee shop.
Okay.
You step up to the counter, you ask for a black coffee. The barista nods, turns around, and instead of handing you a mug, hands you a piece of paper.
A piece of paper?
Yeah. And on that paper is the exact literal chemical composition of caffeine, water, and roasted bean particulates written out entirely in binary code.
Wow, okay. Yeah, I mean, you would probably just stare at the paper.
Right, because it's completely useless to you.
Exactly. Like, it is technically accurate, right? It represents the coffee perfectly at a molecular level, but is functionally useless to a human being standing there just trying to get a caffeine fix.
Yes, and that disconnect between a system prioritizing literal, unambiguous precision and a human who just wants a readable, practical result, that's the central conflict in Ang's notes.
It really is. And we see this conflict emerge because of a very specific programming instinct.
So Ang is writing the command line help text using a Haskell library called optparse-applicative.
Right.
And while setting up that publisher flag, Ang notices this classic annoyance. The default publisher name, which in this case is the Chinese string torture, it has to be hard-coded twice.
Oh, yeah. Developers hate that.
Right. It has to be defined once in the program's actual logic to serve as the fallback value. And then typed out a second time in the help text configuration, just so the terminal can display to the user what that default actually is.
Yeah, and any developer reading Ang's notes will immediately recognize the urge to eliminate that duplication. I mean, keeping code DRY, don't repeat yourself, is fundamental.
That's like the golden rule.
Exactly. Having a single source of truth for any variable prevents state drift. Because think about it, if that publisher name changes in the future, you only want to update it in one place.
Right, because if you update the application logic but forget to update the help string,
then your command line tool will actively lie to your users about what it's doing, which is a nightmare.
Okay, let's unpack this. Ang decides to fix this by changing a single function call.
Right.
The original code used a function called showDefaultWith, which basically requires you to explicitly tell the program how to format the default value for the display.
Yes, you have to spell it out.
But Ang swaps that out for a simpler function called showDefault. Conceptually, to me, it's kind of like using carbon copy paper.
Oh, that's a good way to look at it.
Yeah, you just tell the parser, take whatever the default value is in the logic and automatically print that exact thing in the help menu.
And, I mean, the logic is sound there, but it completely ignores the mechanical reality of what showDefault actually invokes under the hood.
Right.
Because in Haskell, showDefault relies on a type class called show. And the show instance, it is not a UI formatting tool.
It's not meant for the end user at all, is it?
Not at all. It is not designed to make things look pretty. It's a debugging and serialization mechanism. It's designed to generate a string that represents valid Haskell source code.
So it's talking to the machine, not the person.
Exactly. It wants to ensure that a compiler, the machine reading the code, understands exactly what data is present with zero ambiguity.
Which leads us right to the bug. Because when Ang runs the tool to test this carbon copy fix, the terminal output does not display the Chinese characters for shu.
No, it does not.
Instead, the showDefault function inspects the characters and spits out, and I'm reading it exactly, a backslash followed by 25351 backslash 26376 backslash 25991 backslash 24235.
It is incredibly ugly to look at.
It's just a string of numbers. So wait, Why would a program look at standard Chinese characters and decide to spit out a backslash and a string of numbers? What is the show instance actually doing mechanically here?
What's fascinating here is that it is escaping the characters based on their Unicode code points.
Okay.
See, Haskell's show instance for characters has this very, very conservative safety protocol. If it encounters a standard ASCII character like basic English letters, numbers, standard punctuation, it passes it through relatively untouched.
Because ASCII is universally safe.
Exactly. It's safe across virtually all environments. But when it encounters non-ASCII characters like CJK Chinese, Japanese, and Korean characters, it refuses to output the raw character.
Oh, wow.
Yeah. Instead, it translates the character into its raw numeric Unicode coordinate and wraps it in that escape syntax you mentioned.
So that number, 25351, that is the literal decimal value for that first character in the publisher's name.
Yes, exactly. And, most modern developers are used to seeing Unicode in hexadecimal format, like U plus something. But Haskell's character escaping actually outputs the decimal value.
Interesting.
So 25351 is the exact numeric location of that specific character in the Unicode standard. And the compiler does this to guarantee that the output can be parsed back into Haskell code without any risk of encoding corruption.
Because if things get corrupted.
Right. If you pass raw CJK characters between systems with mismatched character encodings, the text can be completely mangled. So by escaping it to pure ASCII numbers, the machine guarantees structural integrity.
So the system is basically prioritizing its own mathematical safety over the developer's intent.
Precisely.
I mean, if you're a user and you pull up a help menu for this XS2 ebook tool, and you see the default publisher listed as a string of decimal escape codes, you are going to assume the software is fundamentally broken.
Oh, 100%. It renders the help menu actively unhelpful.
Right. So this is the trap Aang fell into. By reaching for a macro-level efficiency, just, cleaning up a minor duplication, they handed control of the output to a function that fundamentally misunderstands the context.
Yeah. Show just acts as that robot barista handing over the chemical formula.
So wrestling with show default is clearly a dead end, because the show type class is never going to compromise its strict representation rules.
No, it won't. Aang has to approach the architecture from a completely different angle.
And the notes detail this shift away from relying on the parser's automatic display functions. Instead, Aang moves toward defining a shared constant. So Aang creates a new block of code, defines default publisher, and explicitly assigns it as text, setting the value to Jocha. So how does pulling this out into a distinct constant bypass that whole numeric escape trap?
Well, it breaks the dependency on the show type class entirely.
Right.
By defining default publisher as a standalone text constant, Aang can inject that variable directly into both the core application logic and the custom help string formatter.
Oh, without asking the compiler to evaluate and show it.
Exactly. And furthermore, Aang strictly defines the type of this constant as text to ensure it matches the data model expected by the rest of the application, specifically args.publisher.
Here's where it gets really interesting to me, though. The part of Aang's code that caught my eye wasn't just the creation of the constant itself. It was the extra imports required to actually implement it.
Oh, yeah. The pack and unpack functions.
Right. To make this work, Aang had to modify the file header to import pack and unpack from a library called datatext.lazy. And I keep thinking of this, imagine an office where half the staff speaks an older traditional dialect, and the other half speaks this modern shorthand of the exact same language.
That's a great analogy.
To get the program to agree on what a single word is, Aang basically has to hire two explicit translators, pack and unpack, just to pass messages back and forth.
Yeah, it's a lot of overhead.
So at a machine level, what are these two functions physically doing to the data?
To really understand what pack and unpack are doing, we have to look at the memory architecture of Haskell itself.
Okay.
In Haskell's standard library, the default type for text is called string. But a string in Haskell is just a type alias for a list of characters, which is represented in the code as char.
Okay, a list of characters. That makes logical sense.
It does conceptually, but structurally, it is not a solid block of text. It is a linked list.
Okay, wait, a linked list meaning the characters are not stored next to each other in the computer's physical memory.
Precisely. In a linked list, every single character is stored in what is called a con cell.
A con cell.
Yeah, and that cell holds two things. It holds the character itself and a pointer to the memory address of the next character in the string.
That sounds like a lot of extra work for one letter.
It is. In a 64-bit architecture, that pointer overhead is massive. Like, A single character payload might just be a few bytes, but the metadata and pointers required to link it to the next character that can bloat the memory footprint to 24 bytes or more per character.
Oh, wow.
Yeah, your text is just scattered all across the system's heap memory.
So processing a simple sentence requires the CPU to basically jump all over the physical memory just to find the next letter.
Exactly, and that destroys CPU cache locality. When the processor has to constantly fetch data from totally disparate memory locations, the software slows to a crawl.
I can imagine.
If you are processing thousands of characters in an ebook generation tool, like Aang is, doing it link by link is incredibly expensive.
Right.
Text, on the other hand, is a modern data type. It stores characters in an unboxed contiguous array.
So all together in one block.
Exactly. A dense, continuous block of memory, usually backed by UTF-8 or UTF-16 encoding, depending on the version of the library you're using.
So pack and unpack are not just like changing labels on the data. They are completely dismantling and rebuilding the physical structure of the data in the memory.
Yes. When Aang calls pack, the function is literally traversing that inefficient linked list of characters, extracting the payloads and packing them tightly into a dense, contiguous array of memory.
Wow.
And when Aang calls unpack, it takes that highly efficient array and blows it back out into a scattered linked list. Aang has to utilize these functions because the optparse-applicative library and various parts of the Haskell ecosystem just expect completely different memory structures.
So Aang is forcing the data out of the legacy linked list format into this tight array, just to satisfy the modern parser requirements while still keeping the application's type safe.
Exactly.
But having to manually invoke memory transformation functions just to pass a simple publisher name around your own code base? I mean, that clearly takes a toll.
It's exhausting.
Yeah, and Aang's notes pivot at the end, shifting from this specific XS2 book bug to a deep frustration with the Haskell ecosystem itself.
And if we connect this to the bigger picture, the frustration is entirely systemic. Aang is asking a very valid question. If the linked list char representation is so bloated and so inefficient and requires constant manual packing and unpacking to interface with modern libraries,
Right.
then why hasn't Haskell just made text the default standard in its core libraries?
Which, as a layperson, seems like an obvious upgrade. I mean, if text is the contiguous, memory-efficient standard built for the reality of modern global software and dense Unicode, surely the language maintainers should just update the standard library and deprecate the old linked list model, right?
It sounds obvious, yeah, but you really have to consider the scale of legacy dependencies here.
Okay.
Haskell's core library is called base. It is foundational. And the definition of a string as a list of characters is deeply baked into what's called the prelude, which is the core set of functions loaded by default in literally every Haskell program.
Oh, so it's everywhere.
Everywhere. Every tutorial written over the last 25 years, every legacy enterprise codebase, and thousands of fundamental list processing functions like map, fold, and filter. They all assume that text is a list.
So changing the definition of a string at that base level would instantly break. Basically, the vast majority of the code existing on Haskell's package repository.
It would be a cataclysmic breaking change. You can't just alias it away.
Wow.
So the maintainers of the language are caught between this desperate need for modernization and the absolute terror of destroying the ecosystem.
Are there no workarounds?
Well, there are, like the overloaded strings language extension, which allows string literals to be polymorphic, but they are opt-in features. They are not the default. The default remains the inefficient, pointer-heavy linked list.
Which perfectly explains Aang's pessimism at the conclusion of the notes. Because Aang points to the slow progress of the Haskell stack, recognizing that this architectural friction is not going to be resolved anytime soon.
No, it's not.
Developers are just going to be explicitly importing pack and unpack, manually shifting memory structures around for years to come.
It is a microcosm of the reality of modern software development, you know?
Yeah.
You sit down to solve a trivial UI issue, you just want a default publisher name to display neatly. And an hour later, you are wrestling with memory allocation, Unicode escape sequences, and the ghosts of computing architecture decisions made decades before you even started coding.
It's wild. Looking back at the whole journey today, it really all starts with a simple desire for tidiness.
Yeah.
Aang wanted to adhere to the DRY principle and avoid typing error twice. And that innocent optimization triggered a collision with the show type class, which surfaced that numeric escape bug prioritizing compiler safety over human readability.
Which is such a common trap.
Right. And to fix it, Aang had to bypass the parser's automatic display, build a standalone constant, and explicitly manage the memory structure of the text using pack and unpack. I mean, it is an incredible amount of invisible labor just to render a few characters on a screen.
It really is, and I think it highlights a crucial historical artifact of computing.
What do you mean?
Well, when you look at the tags Aang used on the post like Chinese and Shujk, and you consider the deep frustration with char as the default, it reveals a lot about early software assumptions.
Okay, how so?
If a foundational programming language treats ASCII as the safe, normal default and treats everything else as complex data that must be strictly escaped or manually unpacked just to display properly, well, it tells us exactly who the default user of early computing was assumed to be.
Oh, wow. That's a really profound point.
Right. Modern global developers are still carrying the technical debt of those early localized assumptions. They're writing explicit workarounds just to ensure their own languages render cleanly on a basic command line.
So the infrastructure of the digital world was basically poured for one specific alphabet, leaving everyone else to build manual translators on top of it.
Exactly.
That is incredibly fascinating to think about. Well, thank you for joining us on this deep dive. The next time you see a clean, well-formatted string of text in a terminal, take a second to appreciate the architectural maneuvering it likely took to get it there. Keep exploring the systems beneath the surface, and we'll catch you next time.